In action, the project box looks like this. It is designed specifically so that it will fit snugly inside the bird feeder at my house. The camera and the motion sensor are arranged one on top of the other, and they watch one of the feeder's 4 sides. Here's the conceptual drawing for this project. First, a bird lands in front of the project box, and the PIR motion sensor sends a high signal to the LabView program on the laptop via Bluetooth connection. The laptop then prompts a webcam on the project box to snap a photograph, which is saved as a JPEG file. The laptop should be as far from the project box as possible. Birds are very skittish. Our distance, however, was limited by the length of our USB connection, which was 18.5 feet long. Our project box contains 4 components. First is the passive infrared sensor, or PIR, which uses 2 sensors to detect the movement of a body through their field of vision. The PIR uses a Fresnel lens, which you can see on the bottom left, to concentrate light on its sensors, giving it a 140-degree range of vision. The PIR takes a power supply of 5 to 12 volts and outputs a high signal of about 3 volts. Its sensitivity and the duration of its high signal can be controlled by potentiometers on the rear of the component. Our next component is the 7805 circuit. We wanted to be able to take our system outside, which meant that we needed to regulate the PIR power supply without using one of the big voltage regulators in lab. To achieve this, we built a 7805 circuit that uses a special chip to regulate a run-of-the-mill 12-volt battery and send only 5 volts to the PIR sensor. Our third component is a Vernier GoDirect voltage probe. We use this component to measure the signal coming out of the PIR. Vernier GoDirect devices can connect to a computer through either wireless Bluetooth connections or wired USB connections. We selected this probe because we wanted to take advantage of its wireless connections feature. One thing to note is that Vernier communicates with LabView using specific GoDirect functions. One important aspect of this project was figuring out how to write code that would interface with this probe specifically. Our fourth and final component is a standard Logitech webcam, one that we've used before in lab for Zoom calls. Like the GoDirect probe, we needed to learn how to work with iMac DAX functions that are specially designed for interfacing with a camera. Developing a LabView code that could snap a photograph was one particular challenge of this project. Note that this is the component which needed to interface with LabView using a USB cable. Cameras collect a lot of data. It was more feasible to transmit this data through a wired connection than through a wireless one. Altogether, the inside of our project box looks like this. The 4 components are as follows. The 7805 circuit regulates a 12-volt battery to provide 5 volts to our PIR. Our PIR in the bottom left looks out of the box through a hole in the cardboard. This is what's going to detect our motion. The Vernier GoDirect voltage probe reads a high signal, about 2.2 volts, off of the PIR. And finally, the web camera, positioned over another hole in the box, takes a photograph of our feeder. When we operate our system, the project box nestles inside our bird feeder like this. Note the white paper cylinder around the PIR. This is a blinder that we applied to limit the PIR motion sensing to just the feeder in front of it. Now we can move on to a discussion of code. Here is a view of the LabView front panel, which is the part of the LabView code that interfaces with a user. 2 things to note are the large Boolean light that turns green when a high signal is detected, and the voltage readout below it. There's also a stop button to stop the program. This is very important, and a place to select the camera you would like to use. The rear panel of our LabView code looks like this. First, we have the code to initialize and run the Vernier GoDirect probe. The GoDirect uses specific functions to connect to the probe, start communicating with it, take readings, and then close it. After initializing the GoDirect, we enter into the large while loop of the code. This is going to run continuously. In this section of the while loop, we take a reading from the voltage probe every second. We also check to see if the value read is higher than 2. If it is, we turn on the light and move into our next step. This box is a case structure, which means that it runs specific codes depending on the value you pass to it. This case structure has only 2 cases, true and false. In the true case, we snap and save a photograph. In the false case, we do nothing, and the while loop restarts. Let's take a closer look at the true case. We want to take a picture now that we've detected a high signal. To do that, we use our Save JPEG sub-VI. This function takes two inputs, our camera name and the file path where we want to save each photo. Before we can save a photo, we need to build the file name. First, we add 1 to our running photo counter, so each file name ticks up as we snap photos. Then, we convert that counter to a string and concatenate it to our file path and our JPEG file format. Finally, we convert that very long string into a file path type so that we can pass it to our sub-VI. This is a look at what that Save JPEG sub-VI looks like. These are all iMac functions that work specifically with the camera. First, we open up our camera. Then we start a continuous grab, which is essentially like a video feed. To snap a photograph, we need to create a memory location for the image, so we use the iMac create function to do that. The snap function isolates a single image. Then we write that image to a JPEG file using the file path we created outside in the case structure. Finally, we close our camera. In the event that we want to conclude our program, two things need to happen. First, the user presses the stop button on the front panel, which ends the while loop. Once the while loop ends, the GoDirect stop function executes, safely closing the connection with the voltage probe. It's important that we stop our program with the stop button, or the program won't start up correctly the next time we try. Here are some pictures of our setup. The Birdfeeder is mounted on a high pole, so we could hang our USB cord off of its crossbars. The USB cord was stretched across the backyard to the back porch. On the left, you can see my laptop on a table, and the Birdfeeder in the background, hidden behind the bushes. This wasn't enough distance for birds, though. I found that I had to remove myself from the porch entirely. On the right, you can see my actual viewpoint, hidden inside our screened-in porch. Testing this semester was limited by my schedule, but we did get some good results. Here you can see my first visitors, a molting cardinal and his very pretty girlfriend. The other visitor that we managed to catch was a gray squirrel, who also posed very nicely for the camera. In conclusion, the system worked well, but not perfectly. To improve upon it, I would try to develop some way of alerting the user with sound or a text so that this program can run in the background of a computer. I also would try to universalize this project a bit further. Can we make the project box stand on its own completely? The camera needs to be connected to a computer somehow. We might be able to use a Wi-Fi camera to make the system wireless, or maybe we could run our LabView code on a Raspberry Pi to localize it all within the box. Ultimately, this project impressed on me that development of a strong system may demand several prototypes, not just the one you can build in a semester. It also gave me much stronger confidence with applying concepts useful to physics in creative projects that really sparked my interest.